Okay, so I'm going to switch to the North Pacific and talk about the potential for North Pacific deep water formation and the routing of fresh water into the Northeast Pacific and how that may all relate to Northern Hemisphere climate variability. And maybe the first thing that everyone's thinking with North Pacific and freshwater forcing is that maybe it doesn't matter because it's North Pacific is already fresh. But many models predict the development of a North Pacific, North Atlantic seesaw so that you get deep water formation in the adjacent basin, kind of compensating for reduction in the other related to changes in the salinity balance. And so this is a model by Senko and others, 2004. And the top panel shows an increase in salinity in the North Pacific in response to freshwater forcing in the North Atlantic, whereas the bottom panel shows essentially the response from extracting salinity from the North Pacific. And in general, there are two ways that you can sort of enhance North Pacific deep water formation, and one is to reduce the Pacific or the precipitation minus evaporation balance or the overall runoff, but also you could enhance the meridional flow of subtropical waters into this region. And so what's interesting from this model is that when you actually extract salinity from the North Pacific, you get a stronger North Pacific or Pacific meridional overturning circulation than either the Atlantic deep water formation, but also if you put fresh water in the North Atlantic, the Pacific circulation that develops is not as strong as if you were to just extract it. So anyway, the development of North Pacific deep water has been proposed to occur during the Heinrich stadial during the reduction in the AMOC. And this is a model from Okazaki et al., also showing this sort of increase in temperature and Pacific meridional overturning circulation in the Northeast Pacific. But what's important to keep in mind is that this is sort of the background state that you're operating from, and this particular result is relative to pre-industrial conditions. So this might not be surprising because pre-industrial conditions, Pacific is relatively fresh. But if we look at what's happening in the LGM, many models predict enhanced meridional flow into specifically the Northeast Pacific. And this is an atmospheric model, but this Kim et al., 2008, and this shows the sort of difference in the meridional atmospheric transport between the modern and the glacial. And so really you see the strong heat transport right into the Gulf of Alaska. And this is kind of the difference in surface temperature that results. So you see much warmer temperatures in the Gulf of Alaska region relative to the North Atlantic. And this is also supported by this coupled oceanic atmospheric model, which shows this really anomalous warmth in the North Pacific. This results in even warmer temperatures than modern during the LGM. So really, if we're thinking about kind of Northern Hemisphere heat transport and changing that, turns out the North Pacific may be a really relevant place to think about changing that heat transport. And so this is a highly resolved, it's Unterman et al. Paleometeorology, just showing sort of the visualization of these storm tracks, kind of where you can clearly see the enhanced meridional flow, these storm tracks propagating right up into the North Pacific and the Gulf of Alaska, whereas in the North Atlantic, you tend to have a much more zonal circulation that may restrict the heat up into these. I don't know why it stopped, but that's fine. That's all I needed, really. So anyway, the Gulf of Alaska, it turns out, may be an important place to think about freshwater forcing. And so here are some of the cores that I'll be showing you data from. This is just sort of saying, showing an idealized, say, enhanced meridional flow into this region during the LGM. But then we think about the different freshwater pathways that may be going to this region during the glaciation. during the deglaciation, sorry. And so we know the Missoula floods were these just enormous floods routing from glacial Lake Missoula down through the Columbia River. And there are thought to be as many as 25 events going down through the Columbia with volumes of, say, 1 to 6 spur drips with a maximum volume estimated at even 10 sphere drips for one of these events. And these are dated to somewhere between 19 and 12,000 years ago. But then Lopez and Mix reconstructed sort of freshwater diatoms in front of the Columbia and estimated maximum discharge of fresh water through the Columbia at 17.5. And this also corresponded to a decrease in salinity of 6 PSU in front of this region. So these floods are definitely, huge deglacial floods. But we also have the direct input of the Cordilleran ice sheet. So, there's some talk about getting the ice to where it matters in the North Atlantic region. Well, this is just a pretty direct input to this region that you might have enhanced North Pacific deep water. And so we do observe, in my records and other Gebhardt in 2008 and Davies have observed maximum ice rafting sort of in the same window 16 to 18,000 years ago, largely corresponding to maximum ice rafting in the North Atlantic. There's also the potential for this Arctic routing, say, for the Younger Dryas like Agassiz, and I think that, it's expected that that might go down and impact the North Atlantic circulation, but some models do show that if you lower the sea level pressure enough in the Arctic from fresh water, that you actually might have reverse flow. So in that case, you could have some of this fresh water coming down into the North Pacific. So in order to kind of look at the deglacial surface ocean variability, we just took a multi-proxy approach and reconstructed Deglaciation and 2 species of planktonic foraminifera, as well as the benthic species, and then we did a high-resolution alkanone sea surface temperature record. Then we reconstructed the Deglaciation of seawater, which approximates surface salinity using the temperature and Deglaciation. We have ice-rafted debris records just based on the coarse fraction %, and then we put that in context of water column ventilation using benthic radiocarbonages. And so this is some of the data from these 2 cores, 66 and 26, which I make a compilation of because, strangely, this core ends at about 13,500 years ago, and this one starts at the same time. So it would be nice to have one continuous record, but these provided really high-resolution composite, so I'll take what I can get. Anyway, so this is the Pachyderma sinistrale record composite, so they're meet like right around here, and these are the age models up here, so a lot of age controls. And then this is the Gibeloides planktonic foraminifera Deglaciation, and this lives in a slightly shallower depth habitat, so this will monitor surface salinity changes more likely than this thermocline dwelling species. And so what you can see, at least here in the early deglaciation, is that you have these much lighter values in the Beloides Deglaciation as well as in the Younger Dryas. So that would potentially suggest that there's freshening during both of these times. And so this is the alkanone sea surface temperature record. And broadly, late glacial temperatures are about 5 degrees lower than the Holocene, with clear cooling in the Younger Dryas, and coolest temperatures sort of around in H1 time. But we have these really interesting warm events sort of early on in the deglaciation. This is, of course, the McManus record for AMOC. So these warm events seem to occur, it's really hard it's really frustrating that they don't go farther back into the LGM because we don't have baseline for LGM conditions. So I don't know if these warm temperatures are really reflecting coming out of the LGM, or if this could be some sort of response to, say, reduction in the North Atlantic, and you have an initial resumption in the North Pacific. But then this is the course fraction percent indicating I or D pulses. So I can zoom in on that late glacial interval and look in detail. So this is the Beloides record showing these light pulses. This is the Alcanone record. So you have warming, but then you have these cooling events that actually coincide with essentially freshening. So this is the Delahuetino seawater reconstruction. So this indicates a big freshwater pulse, but you actually get cooling. And those time periods correspond to maximum IRD deposition. So it seems like there's this kind of alternating warming, low IRD, followed by pulses of IRD, cooling, et cetera, in this early deglaciation. So this is kind of similar to the idea of what may be even happening in the North Atlantic. But if we put that in context of just the Delahuetino of the full water column to see, well, maybe what's happening in deeper, we might expect to see a reduced density gradient and a reduced Delahuetine gradient if there was deep water formation. But we really don't see anything obvious during the deglacial interval. I mean, the big event is here, but that's the bowling, and that's likely a warming event. Anyway, so we can move on to the radiocarbon, and this is a compilation of a lot of data, and both new and existing data. And really what you see are the larger benthic planktic anomalies occur during H1, which is or HS1, roughly 17 to 18, and then also in the younger Dryas. So this is both similar to what is expected to be happening in the North Atlantic, but it seems incompatible with the idea of increase in North Pacific deep water during the times when it's reduced in the North Atlantic. And so, this is getting a little bit into some speculation, but I wanted to revisit this idea of IRD, the similar timing of ice rafting between the Cordilleran and the Laurentide. And of course, there are different ideas about the initiation of Heinrich events, internal ice sheet instabilities, and also this idea of subsurface warming, which I think the evidence is, this is really convincing. But at the same time, the observation that we're having, similar timing of ice rafting from the Cordilleran as the Laurentide, to me might indicate, or be suggestive of some sort of top-down climate process that is regulating this melting, this rapid melting. So here's course fraction from Gulf of Alaska. Here's same course fraction from Gulf of Alaska, but on the other side. And then this is the Marcotte detrital carbonate grains. But this is with the volcanic sulfate record from Greenland. And so I just wanted to, throw out the idea that could these intervals of really enhanced deglacial volcanism, so the idea that during deglaciation you have enhanced volcanism, and that is seen in this volcanic sulfate record from Greenland, could that actually create sort of lowered albedo on these ice sheets and contribute to rapid melting? And like I said, this interval here is one of the most sustained. This is sort of an average of the volcanic sulfate, but it shows this really long, sustained interval of volcanic sulfate deposition. So I think I'll just go to my conclusions. So in conclusion, I think that this similar timing from both ice sheets makes it difficult to invoke a North Pacific deep water formation in replacement of North Atlantic deep water formation. So I think at least, if that seesaw may operate in principle between, say, glacial, interglacial climate states, but that during the deglaciation, these episodic forcings might create sort of similar climate changes.
Okay, we have time for one short question.
That one.